So today we are going to study magnetic field at the center of circular coil carrying current. Okay, so let's start how to. Okay, this was our topic. So, so let's draw circular loop. No circular loop. Okay, then I use rubber because to flow a current in that circular loop we need to connect it with the battery. So this. So at the end of the battery, you simply say here it is plus, and it is connected to minus. Okay, this is circular loop, and let us say center is this, and from center the radius of this circular loop, you can take a straight line. So this is center radius. Okay, let's say the radius of the circular loop is r, and let's say the current is flowing in anti-clockwise directions. Now to find out the magnetic field at the center of circular coil carrying current. So let us consider a very small, let us consider a very current element, this yellow one. This yellow one is a current element whose value, let's say the length of that current element is dl. Okay, the length of that current element yellow, and the area vector. Okay, so as per which law? Biot-Savart law. Due to this current element, whatever the name is, maybe we can write. Let's say the current element name is simply write AB. Due to this current element AB, the magnetic field at the center, at distance r, at the center, will be simply V equal to dB is equal to mu 0 upon 4 pi I dl. Let me use a rubber, otherwise sin theta upon r square. Okay, because capital R is that point. Okay, but we have to find the magnetic field due to the whole circular coil, not because of this. So for that, but before we go for that, let us see the angle between the current element. This is your current element, dl is a vector. Okay, so what you can see, and this is, so current element dl and r, the angle between dl and capital R, as you can see, is 90 degree. As we always know, as you are aware that radius is always, line drawn from center is always perpendicular on the circumference. So here it means theta is equal to 90 degree. So after putting that value, we simplify and we call d0 4 pi idl upon r square. Okay, once this is over, now our next step to find out the magnetic field to the whole circular coil, and for to the and to get the answer we integrate it simply. So how to do it? Just put an integration sign, magnetic field to complete coil. Okay, so when you do that, hello. So integration of dB will be, and we'll take a new 0 upon 4 pi outside, and I upon r square also outside. What is left? We left dl. Okay, on further, let's me use a rubber. So now after this whiteboard is very small. So after this, so b is equal to dl. Integral of dl is l. L is the length of the complete circular coil, and so integral of dl is simply is equal to what was circumference of that circle loop. So it's simply the integral of dl will be 4 pi, or 4 pi, no, 2 pi r. So the r will cancel out, and as you want, or you can cancel out. So as per the textbook, we are keeping 4 pi and use as it is. So the net result will simply be mu 0 upon 4 pi 2 pi I. Okay, I'll do it. I'll write it somewhere else. So what I'll use again, so the integral, so it's simply around mu 0 2 pi I upon r. So this is the result, or this is the magnetic field strength at the center of circular coil. Okay, but if there are more than, if that circular coil having more, it's not a single coil. If we talk about n coils, if there are n coils center, then we simply multiply the result with n, so it is 2 n pi I upon r. Okay, so this is the final expression for, and the direction of magnetic field, remember you know it how it is given using a Fleming right hand thumb rule. Fleming right hand screw rule, Fleming right hand thumb rule or screw rule, you can either. Okay, the next problem, because in this problem two questions always asked. First to find the expression, and second is to give the direction of magnetic field. So in this, okay, if the current flowing through a loop is in clockwise direction, let's say as we have drawn a clockwise direction current, then the direction of magnetic field at its center is perpendicular to the plane of paper. Remember, perpendicular to the plane of the loop or plane of the paper, and in inward directions, and in inward direction. To do that inward direction, how will do it? So let's new, so direction, let's write it, direction of magnetic field. ठीक है. So if we take that circular coil, let's say this is circular coil, and the direction of current clockwise. Okay, so the direction of magnetic field or magnetic field lines are like that. Just see it. I use simple other pen. Okay, if it is clockwise, magnetic field direction. If now if you now in this case, if the direction of oi an anti-clockwise direction, then the direction of magnetic field, the magnetic field lines comes out of that paper, comes out of the paper, means it is like that, and they come out of the paper. I'll use a different technique. I'll use different color so that it will be clear. Come out of the paper. Okay, remember. So start, enter, and coming out. This diagram is similar. The direction of magnetic field in case of circular loop is always like that. If the current direction is clockwise, then magnetic field lines directions are perpendicular to the paper or inside the paper. The magnetic field lines enters inward direction, and if the direction of current is anti-clockwise, then magnetic field directions outward direction. This is inward direction, this is outward. By this you can remember, or I'll write. I'm little bit difficult to. Okay, outward. Now let's start the new one. Now let's see the new topic. Now this topic is very much important than the earlier one. Let me reckon the okay. For that, now our new topic is magnetic field at the point. So let me write it. So that magnetic field at point magnetic field at a point on the axis of circular current. Okay, so our next magnetic field at a point on the axis of circular coil carrying current. And so let's consider a circular coil whose radius is capital R, and so let's draw it. Okay, and let's choose. Okay, so this is axis. It's passing from its center. Okay, there are two axes. One is okay. Now here in our case, the point P is anywhere on this axis. Let's make it. Let's say point P is here. So here we have to find the magnetic field due to this circular coil. And remember, this is an axis passing through. Now, what I'll suppose to do, let's name it. To find out magnetic field at point P, again we have to choose. To apply the bias vector, we first choose smaller portion of it. So we have to first very smaller portion. Okay, the top and bottom. Why I have chosen? Because of the symmetry. So let's take it. Okay, let's take that current element name AB, and this one A dash B dash current element. Current element. So now from this current element AB, best way I use is and from bottom as well. Okay. Now let's say the distance is point P. Let's name it. Remember, this is point P. This with this is a point P. So let's the distance from AP is R, and this is also R. And from the center of the circle, the point P as distant, let's say X. Okay, just remember X. This and the radius of circle is we talked about. The radius of circle is capital R. Now first initially from current element AB, the magnetic field at point P will be given by according to Biot-Savart will be equal to dV is equal to, you remember, nu 0 upon 4 pi dl upon small r square, because point P is r distance away from current element AB. Similarly for this is for AB current element, and it is same for BD. Okay, A dash B dash as well. Why I have not put sign? Because theta is 90 degree and sine theta as we know it is sine 90 is 1. If you look at AB and the current element AB and the AP line, you will find they actually they look like this. So the angle is 90 degree. Okay, that is why I choose. So this is value. The same value is for other element also. A dash B dash as well. To cover the whole chakra, we have chosen it. Now, so I'll first rub it because I need a space here to draw out. Now the at point P, the direction of magnetic field will be as according to right hand thumb rule, Fleming's right hand thumb rules. So the hand thumb rules. So let's draw it. The right hand thumb rule, the direction of will be like that. I draw with some different vectors. Okay, because two current element, so direction of magnetic field will be opposite to it. AB, due to AB, it is okay. Due to AB, this is the magnetic field value, and due to A dash B dash current element, this one. Now, after getting the value, final value, but you are remember, you can see the diagram. AP, let's name it. This is okay. Let's name it. First use space is very less. I'm just reading. Remember, this one is dB. So now PQ. Shut your mouth. So PQ. तो लड़का so P2 so we can PQ vectors which is in dB we can break into why I'm writing okay one for PQ and one for PR. Achha, now but to get how to get it for that let's say this is angle phi 5 because we have already chosen and this is also phi. So these angles become phi. Okay, these are phi, so the horizontal component will be dB cos phi. Remember horizontal component here also dB dash cos phi. I just name it because and the vertical component I put two arrows here because both are in the same direction. So dB sin phi. Okay, it is very less space. Sin phi dB sin phi. Okay, so as you can see from the diagram these vertical component, okay, are cancel each opposite to, so these vector will cancel each other effect. So what is left? Only the horizontal component dv sine phi. So the total magnetic field, so magnetic field, so these two all summed up. So intensity of magnetic field due to circular loop at point P will simply be given by integral of dB sine phi component. Okay, it's not side dB sine, because dB and dB is the same. Now we have to substitute the value of this dB from up. So after substituting, so I'll use rubber. So it will be ideal upon r square sine phi. Okay, integral. Again I use rubber. So so what sine phi? How now? Next step is to find out sine phi from the triangle. As you can see, triangle A P, and from center this triangle is right angle triangle. You can simply find out sine phi from this vector, this triangle. I'll just use a different pen to show you. From this triangle, sine phi can be easily be calculated. Sine phi will be what? Perpendicular upon base. So perpendicular will be r and base is x. Perpendicular upon hypotenuse. So capital R upon small r. So now you got the value. Now this value will substitute over here. So in doing that, simply substitute over here. So r upon r. Now further using now you can take out the common terms whatever you put. So mu 0 I r 4 pi r cube integral dl. Now integral dl means the length of the circular loop, and then we know the length of circular loop is how much? 2 pi r circumference. Do we substitute that value? Integral of dl is remember we are not cancelling 2 pi and 4 pi because 4 pi just to make it separate. So let me, okay, now one more thing. So now we can simplify further by Now if you look at again into the triangles, this triangle, this right angle triangle, in this triangle r, x and r, capital R, okay, that is are related by small r by using under root x square plus r square under root x square plus square. So by using that we can replace this small r, this r. So now in simple, so the final solution magnetic field, I simply use a red. I have to rub it. I'll rub this down. So the power is 3 by 2. Okay, let me again very few space. So square plus r square 3 by 2. Remember why it is 3 by 2? Power 3 by 2. So the complete solution. Okay, so this is the complete solution for magnetic field at point on the axis of circular coil carrying current. Now again, and if again here last section, if there are more than, if there are n turns, then it is we simply add up to n. We simply add up n. So 2n pi r square. And to understand this result in graphical method is the best way. So let's say it. So if I'll take this center and x-axis, and here is 0, x is 0. What was x? Distance from point P. Means as we know it that x is equal to 0, the magnetic field at center of pole x maximum, but as we are moving, that means point P shifted from center to this far, the magnetic field decreases. You can see it. on either way, in both the ways, whether you move right hand side or left hand side. Okay, there are some other special cases also. This graph is very helpful. Means when point P is at center, then magnetic field will be maximum due to this coil. But when point P is travel along the axis, then magnetic field decreases. But parabolic, remember, huh? No, actually, the direction of magnetic field. This magnetic field will help us to find out the directions. Now, let's circle and current anti-clock. Anti-clock. Okay. So at center, if you remember, the magnet. If you remember that today I said in the beginning that magnetic field when up outward means the magnetic line forces come from and goes like that. Okay, when it is anti-clockwise direction. So this vector is north. So on the basis of circular coil, so each circular coil, now there is a one more conclusion. Each circular coil in which current is flowing is like a magnetic is behaving like a magnetic pole, depending upon which magnetic like a pole, it depend upon the direction of current. Let's draw it. Let me draw. Okay, in this loop, if current is anti-clockwise, anti-clockwise direction, so this loop will act as north pole. You can remember simply north top and arrow. Okay, and if we choose, okay, on this here for this, if the current in clockwise direction, then arrow south pole. So the loop in which current is in clockwise, the loop in which current flow in clockwise direction act as south pole, and the loop in which current flows in northward in anti-clockwise direction, it acts as north. So this is the conclusion to find out the polarity of magnetic field. So where it is helpful, let me explain. Let me give a simple direction. Cancel. Okay. Let's say I draw helix. This is a coil. Okay, coil is usually like that, and from this end, current be enter here, and it leaves here. Your battery is connected plus minus. I'll say plus, this is minus. So now you can see in this coil the current is in clockwise. So let's finish it today. We'll study tomorrow.